Water guns. Super soakers. No matter what you call them, these things have been a staple of summer fun for decades. But have you ever stopped mid water fight and wondered how these things actually work? How could a piece of plastic shoot a powerful stream of water all the way across the yard? What kind of magic or engineering is taking place between that little storage tank and your friend's very surprised face? Today, we're breaking it all down. So grab your goggles, maybe take cover, and let's dive into the science behind one of the most beloved toys ever made. Okay, so before we dive into a lengthy explanation of Bernoulli's principle, let's just first discuss about what are the components in the water gun and how do they work together. So we start off with the pump, which is directly connected to the water tank, and these two are connected through something called the pipe or the hose. All of these components basically work together to eject water at high speeds into the atmosphere through the nozzle at the end.
Yeah. So how all this works is actually really simple. So first, when you pump the gun's pump forward, what happens is that you create a lot of negative pressure in the hose area. And then because the water tank has a lot higher pressure than the hose, all of this water comes through into the hose and into this little area right here. And then when you pump the pump back, this then moves forward and creates a lot of pressure in the hose itself. Now, all of this water wants to go to wherever there is less pressure. And where there's less pressure is out through the nozzle and at your friend. All of this relates to Bernoulli's principle, which is one of the fundamentals of fluid mechanics.
This is Bernoulli's principle. It describes the behaviors of three key components: static pressure, dynamic pressure, and hydrostatic pressure. As you can see, the sum of all three of these components is constant throughout a fluid.
How does this affect our water gun? Well, what we need to know first is how the values all affect each other within the water gun.
The most important relationship is between pressure and velocity. When pressure increases, the fluid velocity decreases. This is because as more pressure is pushing on the fluid, it opposes the motion greater.
Yeah. But inversely, whenever the pressure decreases, the velocity actually increases. And that's how the water gun works. It's because the water kept going wherever there was less pressure until it eventually leaves the nozzle.
Over here on this side of the equation, you can see that elevation does play a role in changing these values. But inside a water gun, it actually doesn't have that significant of a role due to the small size of the water gun. The elevation difference usually isn't that much. And in fact, in our water gun, our water tank is essentially at the same elevation as the nozzle. It's essentially just on a straight path, and so there's no elevation difference to consider in our specific case.
Yeah. But to demonstrate how you can utilize Bernoulli's principle to solve problems, we can set up an experiment to calculate the static pressure that's built inside the pump of the tank.
This experiment is actually fairly simple. All you need are four key items: a table, a yardstick, scotch tape, and a water gun of your choice.
To set the experiment up, tape the measuring stick to the table with the beginning point of the stick at the edge of the table. This is so that you can record the distance traveled by the water without the stick moving. Then, set up a camera of some kind to record the test. For this test, we used a Samsung phone. To conduct the experiment, load up your water gun with room temperature water, hit record on the camera, and start firing the water gun with the nozzle at the same point as the beginning of the measuring stick. This point will be your origin point. After you fire the water a few times, stop recording and see how fast the water traveled across the measuring stick. Our stick is 3 feet long, and it took on average about 0.2 seconds for the water to travel 3 feet. If we divide 3 feet by 0.2 seconds, we get about 15 feet per second. Then, we can convert to meters per second, in which case we get 4.527 meters per second. This is the final velocity of the water.
Now that we measured the exit velocity of the water coming out of the water gun, we can finally connect what we observed to the physics that actually make it work. As mentioned earlier, Bernoulli's principle states that the summation of static, dynamic, and hydrostatic pressure is constant. From this relation, we can write an equation connecting 2 points along this streamline under different conditions. Point 1 represents the conditions inside the water tank, and point 2 represents the conditions right at the exit nozzle. Now, this might seem complicated at first glance, but we can actually simplify the equation down a lot right off the bat. First, we know that there's no elevation difference between the water tank and the nozzle of our water gun. This means that we can completely eliminate the hydrostatic pressure parts of this equation, as they rely on height. Next, we can approximate the water velocity inside the tank to be 0, since the water at the exit is moving at such a higher rate in comparison. We can also acknowledge that since the nozzle exits into the atmosphere, P2 will be 0 as well. This leaves us with just P1, the pressure inside the tank, and the dynamic pressure at the nozzle. We just found out that the exit velocity is around 4.572 meters per second, and we already know density of water is 998 kilograms per meters cubed. So, to determine the pressure inside the tank, all we have to do is plug in our values into the right side of the equation and solve. And there you have it. Every time we pump the water gun, we were creating 10.4 kilopascals inside the tank. Now that's a lot of pressure. Today, we've shown you Bernoulli's principle. It's one of the fundamental principles of fluid mechanics, so it has many potential applications, from open channels to water pipeline systems to even water guns as we've shown today.
We hope you learned a little more about fluid mechanics today. Thank you all for watching.